Good evening, good morning, good afternoon, everybody who have joined from different parts of the world. Welcome to hypothesis testing, one of the most important topics in statistics world. My name is Rohit Krishna, and I work for JP Morgan as a data scientist. I have total of over 5 years of experience in data science field. I've worked on machine learning models, the data analysis part, the data science visualizations and stuff. Today we'll be dealing with hypothesis testing in general, and I'll start by sharing my screen and then we can take forward from it. Let me start by discussing an example. Usually, suppose that you are working for a manufacturing drug manufacturing company, where you are a part of a research team which has come up with a new drug, right? The theory is done. You're done with the manufacturing, but you want to test how this drug is affecting, or what is the effect of this drug on different kinds of people. In that scenario, you cannot really go to each and every person that the drug is being tested on. Rather, you collect certain samples from the entire population and then try to understand the behavior of that sample, and then you attribute that behavior to the general population, right? So hypothesis testing is very important when you're dealing with samples. You try to understand its behavior, and then you try to map that behavior to the entire population, right? What can you expect from this session is that the general intuition behind hypothesis, like what is it, what is its role and importance in the statistics or research field, followed by, we'll deal with certain bit of mathematics on it, because we will be solving certain examples, how a particular hypothesis test is being conceptualized, how can you come to a conclusion on your data, and then we'll discuss about one of the most confusing topics, I would say, p-value and significance values and confidence intervals in statistics subjects. And then followed by that, we'll discuss various types of hypothesis tests that are available and its applications, and one of the basic machine learning model called linear regression. Now, I understand that we have people who are new to data science, new to statistics, and some of them might have already know what hypothesis testing is all about. The session is named Hypothesis Testing A to Z, but by that I mean we will try to conceptualize, we'll try to dig deeper into the intuition behind the test, rather than touching upon all the tests that are available in the industry. So we'll take z-test as an example. We'll try to solve certain problems, but once at the end of the session, I believe that you would be able to you'll be able to understand the terminologies of a hypothesis test, the process, how we do it, and you can attribute or you can map those concepts back to any hypothesis test at hand, right? So when you look at the formal definition of hypothesis testing, right? When you look at Wikipedia, this is the definition that you find: a method of statistical inference used to decide whether the data at hand sufficiently support a particular hypothesis. What does this mean? As I said, suppose you're looking at election results, right? But before election results, you often find these surveys that news channels or certain third-party organizations do. It's very difficult to go and ask the opinion of each and every person in state or in the region or in the country, right? Rather, what they do is they collect samples, they pick few people from different backgrounds, and then base their analysis, base their results on their opinion. Okay. So statistics, if you look at whole statistics world, it is divided into two parts. One is descriptive statistics, and second is inferential statistics. Descriptive statistics deal with certain numbers that describe the group. Say you are having 50 students of a class, right? You are trying to identify what is the average age of the students in the class, or what is the average marks scored by the students in the class, or what the maximum marks scored by a student in the class, right? So all these are kind of describing your data at hand, and the results are only attributed to that particular data, right? So you're trying to describe the data with certain numbers. That is part of that is part of descriptive statistics. But inferential statistics is where you collect certain sample. Let's take an example of the same example where you have 50 students in the group. You try to understand their behavior, and you base that understanding or the characteristics of that group and infer something about the population at large. Say you're trying to, you have picked 5 schools in a city, you're trying to understand their behavior, And based on the results of those 5 school samples, you might be coming to a conclusion and deciding that this particular behavior is common across all the schools in a city or in a region in a country, right? So that's the difference. Descriptive statistics deal with only the describing the group at hand, but in inferential statistics, you try to infer about the general population, right? I see a question. Okay. Hello. I'll try to speak louder. Right. Moving on. Say we have, as I said, population is very large, and you try to pick samples, right? Again, coming back to the same election results example, if you want your analysis to be correct, what you try to do is you identify samples with different with good representations across different groups. Say you have, you cannot go to only rural areas and get their opinion and base your analysis or base your results that this is going to happen in the election result. No, you if you want a accurate result, you would be needing survey results from different ethnic backgrounds, different age groups, different ethnicities, different occupations, right? So the idea is that when you sample your data from the population, that sample should be a good representation across all the subgroups in the population, right? If you look at this population diagram, the diagram that is in the slide, I'm picking, if the color is the different characteristics, right, different attribute of regarding the population, you see different colors being picked. So that is basically representing your population well. And this is really important because your entire analysis is based on the sample that you collect. And if that sample itself is not a good representation, you cannot base your results and attribute it to the population with good confidence, right? Now, why is this important? Why is hypothesis important, and what is its role? You take any research paper now, whatever experiment they conduct, take any field, be it manufacturing, be it clinical trials of medication, be it drug discovery, or machine learning model hypothesis, right? Take anything. At the end of the experiments, you find a section where there's a statistical evidence that with certain degree of confidence we are basing our results, and this is what is going to happen, right? So this became a common conclusive framework, I would say, for any researcher, for any statistician, to take the research forward, and also for the general public to build the confidence on the experiment, right? With this knowledge at hand, what we'll try to do is we'll take certain example. We'll take an example of a particular data distribution and try to identify the descriptive stats about that, the mean, the standard deviation about that, and what will be our building block for going to a hypothesis test, right? And this would have certain maths. I would solve certain problems, and if you're comfortable, if you're interested, you can have your pen and paper at hand, and then we can solve it together. Okay. I see a question. What if the sample we collected was biased or incorrectly collected? Yes, as I said, Kirti, your entire analysis is based on sample. So it is our responsibility to take sample with good representation across subgroups. If not, then the analysis that you do or the results that you conclude cannot be attributed to the general population. It should be confined to the sample that you have collected, or the subgroups from the sample that you have collected. Right. Right. Let's take this a simple distribution where you have data 10, 12, 14, 15, 17, 18, 18, 24. You have 8 data points, and you're trying to, and let's identify what is the average and standard deviation of this group. Okay. So you know that average, probably, 1 second. Yeah. So to calculate mean or average of the sample, what we do is we add all these numbers and divide by the number of data points, right? So it should be 10 plus 12 plus till 24 by we have 8, right? So the mean here would be 16. Okay. Now this is the average value that this data represents. Now there's another term called standard deviation. What is standard deviation is, if you look at the mathematical formula, it would be somewhat like this: x minus x bar whole square by n. Now x bar here is the mean, which is 16 in our case. Intuitively, what standard deviation gives us is how deviated your samples are or the data points are from the mean value. Okay, let's say that in this case our mean was somewhere here 16. Okay, let's calculate the standard deviation for the sample first, and then we'll see what does that intuitively tell us. So this would be 10 minus 16 whole square plus 12 minus 16 whole square. So what I'm doing is I'm taking each sample, each data point, sorry, and then seeing how different it is from the mean divided by the total values. Now this would give me a value which is close to 4.03. Let's assume this is 4. Okay. What standard deviation tells us? It tells us that from the mean value of the data, how on average, how deviated are the other data points. Okay. So if you see here, if I take each example, 15 value is one number away from my mean value. 14 is two numbers away. The difference between 12 and 16 is 4. This is 6. Similarly, on the other side, from the mean value, 17 is one number away. From 16, it would be 2, 2 again, and 16, 24, the difference is 8. Okay, so this actually gives us how is your data spread across the sample or your data. Okay, now suppose if my deviation was say 2 instead of 4, my mean value being 16, I would say that most of my data points would be concentrated on between 14 and 18. Okay, this would be my general distribution, and values below 14 and 18 would be of less probability. Okay, I can say that most of my data distribution is lying in this region. So standard deviation gives us the average deviation, how my data is spread. That okay. Now, when you talk about normal distribution, as I've taken examples of say students, the average age of students, or the election results, any general behavior that you talk about, it should follow a normal distribution. Okay, what normal distribution is that majority of your data samples would lie in the middle half of the region, the middle region, and as and when you go to the extreme end, the probability of these values occurring would be less. Okay, you can see most of the data is being concentrated here. Now we will use this distribution as our base to start our hypothesis analysis, and there is something called CLT, which tells us that if your data samples are greater than 30, right? If your data samples, if the number of data points in a sample is greater than 30, the distribution is assumed to follow a standard normal distribution. Okay, so once we take this as a criteria, we can start our math and then pick one example. We'll deal with one example and do our math. So let's start with an example, and we'll build the intuition behind the hypothesis, how we do it. We have a medicine that is being manufactured by a company, and each pill is supposed to have 14 milligrams of the active ingredient. Okay, so we are manufacturing a pill which is trying to work on certain illness, and each pill is composed of different ingredients, right? Now, one of them would be very active, very important part of the drug. Say that's the composition of that drug would be 14 milligrams. Okay. Now, the researcher or the drug manufacturer is aiming at this composition. He or she wants the active ingredient to be of 14 milligrams out of this drug. Okay, but practically speaking, when you manufacture a drug, there are a lot of things that you need to factor in. One is you manufacture the drug not just in one machine. There might be multiple manufacturing production lines. So are all the machines same, producing exactly 14 milligrams of active ingredient? Is there any difference? Is it 14.01? Is it 13.95 milligrams in the pill? And if there's a difference, if there's something away from 14, is it acceptable or not? And we need to be very confident about this because, of course, when this drug is being given to a particular patient, if the active ingredient is missing, either it would cause side effects or it would not work on the illness, right? So To back up our analysis or our intuition behind this using statistics, we can use hypothesis testing, right? Now, in the previous example that we have seen, in this example, we know that our most of the distribution will lie in the middle half of the region, right? Now, let's take 14 milligrams as a mean value. Like this is what we are aiming for. Now, there is a very good possibility that our manufacturing line is producing drugs which is probably 14.01 milligrams or 13.95, 13, 15, right? So you know that even though the manufacturing production line is bit errorless, you know that most of the distribution would lie here, right? Intuitively. And the probability that your manufacturing product line is producing drugs with 18 milligrams or 10 milligrams is less, right? With certain degree of confidence. Now taking this region, right, there must be an acceptable threshold that you are okay with. Say, so the drug manufacturer is saying that, okay, my drug need not have exactly 14 milligrams, but even if it is 14.95, I'm okay with it. Okay, or even if it is 13.60, I'm okay with it. But if it is 20 milligrams out of the pill, that is of concern, because this is not the general behavior or the behavior that the manufacturer is aiming for. Okay, so to test this, he cannot. So say the manufacturing industry has produced say 10k pills. Now we cannot pick each sample separately and test what is the active ingredients weight in each sample. Rather, what we do, we take say 100 samples from this 10k samples, from this 10k population, and then try to identify the behavior across these 100 samples. All right. Now let's say for the 100 samples, let me erase this. All right. So let's say for the 100 samples, my mean is here. My distribution is somewhat like this. This is 18 as an example. This is 10. Okay. Me being the drug manufacturer, I know the effect of drug. I would say that if my drug is consisting of at least 16 milligrams or 12 milligrams, I'm fine with it. But if it crosses this region, if it comes into this region, then I would really worry about the drug. Okay. Similarly, I want it to be at least 12 grams, but if it is less than 12 grams, that is of concern for me. Now, when you have 100 samples at hand, what you do is you find the average value of the active ingredient. So say that is somewhere around 15.2 milligrams, right? Your actual aim is to get 14 milligrams, but after manufacturing your drug is, you have taken 100 samples and the average value is 15.2 milligrams, which is somewhere here. Okay. Now, since this 15.2 milligrams is less than your threshold value, less than your acceptable, within the acceptable region, you are still okay to go ahead with your manufacturing line. There's no problem. But what if after you collected the samples, instead of 15.2, your average value has turned out to be 17.6 milligrams, which is somewhere here. Okay. So this is a general behavior. This is a behavior that you are not expecting, and you want to reject your hypothesis that my active ingredient is 14 milligrams of the production line. No, that's not. So you have some concern, and you need to go back and revisit your manufacturing line or whatever composition you're dealing with. Okay. So moving on, if you look at the red line, right, this is called the significance value in statistical terms. Okay. And if your samples average value or whatever metric that you get from the samples, if it is within the acceptable range, you accept your null hypothesis that my drug is okay to be delivered to the general public. Otherwise, you reject your null hypothesis that 14 milligrams is not what I see, and I need to work on it. Okay. So the intuition behind hypothesis testing is you take a population parameter you collect samples from the population, and then you identify, you see the difference. If the difference between your assumed value, which is 14 in our case, and the sample estimate, which was 17.6 in the previous example, right? If the difference is large, and if the difference is more than what your threshold is, then you reject your null hypothesis about the population, and you revisit your analysis or experiment. If the difference is small, as in the previous case, which is if it is 15.2, which is within the acceptable threshold, you accept your null hypothesis and you go ahead with your manufacturing. So there's a question. Initially, when we claim something as null hypothesis, is that analysis based on population or sample? Null hypothesis is always based on population, Kirti. That's what it is. Like the general behavior. You say that children prefer chocolates more than adults, right? That's the general behavior you know about the population. So always base your null hypothesis based on population, and you collect samples, do some math, do some analysis, statistical analysis, and conclude the behavior to the population. Okay. How to decide null hypothesis and alternate hypothesis? I think that's answered anyways. What is the percentage of sampling from total population? Is there any specific values? No, I would say there's no percentage. It depends on the size of the population, size of the sample. But it's always advisable that you collect samples with more number of data points. The larger data set you have, the data would be approximating to normal distribution, and then you can apply this test with good confidence. So if you look at the books, right, you would say that the samples should be greater than or equal to 30 data points before doing any hypothesis test. If the samples are less than 30, there are still other tests that you can apply, but it's better you have more than 30 data points. Right? Yeah, so hypothesis testing, I hope the intuition is clear. You check how extreme the value is from your sample, from the hypothesized value, and if the difference is large, you reject your hypothesis. If the difference is within the acceptable range, you accept it. Right? So formal definition about null hypothesis, it's a statement about a population parameter which is believed to be true, and alternate hypothesis is the statement that directly contradicts the null hypothesis. I think this is explained already. Now in the previous example, what would be our null hypothesis? It would be that my average value, composition of active ingredient in the drug is 14 milligrams, whereas my alternate hypothesis would be the average value is not equal to 14 milligrams. It can either be less than 14, it can be greater than 14, but it's definitely not 14. Okay. Now, when you talk about the distribution here, as I said, there is a certain threshold that within which you can accept your null hypothesis, right? But these regions, right, where if your difference is falling in this region, these regions are called rejection regions, and the value here, these values are called critical values. Okay, so once your difference is falling within this critical region, you reject your null hypothesis. Let's take the example previously. We had numbers of say 10, 12, 14, 15, 17, 18, 18, and 24. Okay. As I discussed in the introduction, right, we would be dealing with z-test as an example, and then we'll build the entire hypothesis on that. Now, what is actually z-score? Z-score is nothing but the number of standard deviations away from the mean. Say in previously our mean was 16. Okay, so each number here can be represented in terms of a z-score, in terms of a standard deviation. Like how many standard deviations is 17 away from 16? How many standard deviations is 18 away from 16? Okay, so what are we doing essentially? We are trying to convert one range of values into a standard range. Okay, into a z-score. Say for 16, if you apply this formula, right, where x is your actual value, mu is the mean of the data distribution, and sigma is the standard deviation. If you remember, standard deviation for the sample was 4 from the previous example, and mu was 16, right? Now this series of numbers like 10, 12, 14, 15 can be represented with z-scores. Okay, 16 if you substitute 16 here, 16 minus 16 by 4 would be 0. So the z value for mean would always be 0. Okay, Similarly, if you substitute 17 minus 16 by 4, it will be 1 by 4, which is 0.25. 18 would be 0.5, 20 would be 1, 24 would be 2. Similarly, you can calculate for these values will be coming into data distribution, right? What did we do essentially? We have mapped or maybe converted this data into a more standardized way. So for this example, we have got range of values between 10, 12, around in 2-digit numbers, right? Say we have another example where we have values ranging from thousands to lakhs, right? Even then, to standardize, there's something called Z table where we find for probability distributions. So to standardize our analysis, we will first convert those our data points into a standard scale, and then use these values to back our analysis. The certain questions, I'll try to answer them. Is there any way that the sample taken is biased or outlier values and the actual values may fall in the allowable range? Biased or outliers and the actual values may fall in the allowable range. Yeah, if I understood the question correctly, you definitely need to see if your sample is consistent of outliers, and there's a way to identify those outliers in statistics, which is multiple ways. But if you look at the box plot distributions, you can find outliers, right? But it's our responsibility to take sample that is a good representative of the population, as I already told you. Parthasarathi. Next question: can hypothesis testing be used to validate the variables you're using to build a machine learning model? Yes, you can. When you're trying to build the hypothesis or the general intuition behind any regression model, right? So I think I'll be dealing with this in the last slide in this lecture. Well, let's hold on till then. Where did you just get the value of Z? So Z is being calculated here. So Z is a representation of, it's a mapping of your original values into a standard value, right? So X minus mu by sigma is this. Now suppose my data point is 10 and my mean value is 16, as I said. So I'm substituting 10 here. Mean mu is 16, standard deviation is 4. So you get your Z value to be minus 6 by 4, which is minus 1.5, right? So that's how I get my Z values. So another question: if conducting survey in a population is ideally impossible, then how can we say some value as population mean? So that's a general assumption. So it depends on the kind of problem statement that you're working with. If it's a drug manufacturing, then you know what your drug should have, and then you based on your medical knowledge, right? You know that this is the acceptable, or this is the composition that you're aiming for. So that becomes a population mean or a hypothesized value. It need not be mean always. That's an example, but there's always a hypothesized value from the population from your general understanding, right? What Z-score tells us mean why we calculate. Okay, so Z-score tells us how deviated your data is, or how deviated your particular value from the mean is. Say I'm telling you that, okay, I have a class of 50 students, and the average score scored by 50 students is 75 out of 100. Okay, this is the average score, which is just a single number trying to represent the entire class. But I want to get more information about this the class students, right? How their score values. I know that out of 100, 90 is the maximum score. 35 is the minimum value scored by the student. Okay. Now this gives me an intuition about, say, my data is ranging from 35 to 90, with 75 being my average value. But I want to know the standard the deviation in the data, like on average, how much is each student away from the mean of 75. So that's what Z tells us in terms of the standard deviation. So if the standard deviation for this case is, say, 16 marks, I would say that most of my data points are 16 marks away from the 75 value. So that's what Z tells us. Hope I answered the question. Okay. So coming back to this point, once we have the data distribution at hand, like in this case 10, 12, 14, 15, a standard scale which is -2, -1, preferably -1 to +1. Okay. All right. Once we calculate the Z-score, how does this score help us in identifying or concluding a hypothesis? Say in the previous example that we have dealt with. 14 milligrams was our mean value. Okay. We are mapping it after the after converting these values to z-score. The mean of the 14 milligrams would be 0, right? Somewhere around here. Yeah. So this is my mean. Now I want my drugs to be concentrated mostly in this area, which is the middle half of the region, which is within the acceptable threshold, as I discussed. What we do is, once we collect samples, right, we come up with a z statistic. And once we come up with the z statistic, we'll see whether that particular value is falling. Suppose this is the critical region. Once we calculate the z statistic, if it is within this region, we accept the null hypothesis. If it is falling in this region, we reject the null hypothesis. It's not actually accepting the null hypothesis, but we are failing to reject the null hypothesis. We never accept the hypothesis, but we fail to reject it. Okay. Now I'll deal with the z statistic in detail with an example in the next slide. But as I said, you identify critical regions and then you try to conclude whether you can accept or reject the null hypothesis. Now, based on the kind of problem statement that you're dealing with or what you're trying to answer, right? You either accept your, the rejection region would fall either on one side of the distribution or it could be on the both sides. Let me give an example. Say you have there are incoming admissions for a university, right? And you're checking the average score scored by the students in that college in the entrance exam. You say that on average I would only accept students or my university is consisting of students whose average score would be 110 in the entrance examination. Okay, that's a general belief or hypothesis. Now you have taken sample from the population, from the students, and then saw that the sample suggested that your average score is 120 rather than 110. Now, in this case, your actual value from the sample is greater than your null hypothesis value. Okay, so that's when you take the right side, the right end of the distribution as the rejection region. So your null hypothesis is that states that your average value is 110, but your actual data is saying that it is 120, which is greater than your average value. So you look at this part of the region and see if this 120 is falling within the acceptable region or if it is falling above this region. If it is above this region, then you reject your null hypothesis. Similarly, say take the same example. You want students who have average score of 110, but your actual data is suggesting that you are getting students which are of having 90 as the average score, right? Which is very far away from your from the score that you desire in your university, right? So if it is very away from that, then you probably look at your admission and then see why are these students coming up. Okay. Taking previous example for two-tailed test, where the mean value is this, but your hypothesis value is this one, but your actual data is suggesting that this is not equal to 14. It can either be greater than 14 or less than 14. So here you're interested in both the sides of the data distribution. So this becomes two-tailed. Since you're dealing with only one tail here, these two are called one-tailed tests, and the bottom region is called two-tailed tests. Okay. I see certain questions, comments. Is there any statistical technique for selecting the sample from the population? There are different sampling techniques. So you have random sampling, you have systematic sampling, probably 4 or 5 kinds of sampling, and it depends on what is the kind of problem statement that you're dealing with. Sometimes random sampling is desired, sometimes you go with systematic sampling. So it's all in the hand of the researcher which kind of sampling is used. Does z-score distribution normalizes the data? Yes, it does, because you're scaling your data within the standard deviation, right? It definitely normalizes your data. Can the data points which are way too far from zero be treated as outliers? You cannot completely say that, Samiksha, because it depends on how your data values are distributed. Say most of the data is between -20 to +20, and you're finding a value which is 40. Okay, now that becomes an extreme data point. But what if your distribution has values from -40 to +40 and you're finding a value which is 45, right? So 45 is not as extreme as in the previous case, right? So in the second case, it might not be an outlier, but there are statistical techniques to identify whether a particular data point is considered outlier or not. Is it used by statisticians only or data professionals also? It is used by data professionals. It is used by researchers in the medical field, in the manufacturing field. So this deals with any data, right? I mean, be it any industry. Once you have data points, you are trying to understand whether this data point is the representation of this data point is being done properly. The analysis of the experimental results on the sample is according to your belief or your desire or not. So it can be used by anybody. So Ria asked the question, there is a possibility that the data value in dataset is biased or values are outliers. That case is skewness case, either right skewed or left skewed, but there sir has considered normal distribution. Okay, yes. So when you're trying to, good question, Ria. Let me come to that. Suppose your data, your data is not always normal in reality, right? Let me erase everything. All right. Suppose you find a data distribution like this or like this, wherein your lower values are of higher probability and your larger values are of less probability. Okay. Now this is a population or this is a sample set. Central limit theorem, there's something called central limit theorem, which says that if you collect good number of samples from the population, the average metric or the sample statistic that you're dealing with, right? If you're dealing with more than 30 samples, this will approximate a normal distribution. Because of this theorem, we are assuming our analysis, we are basing our z-test based on the normal distribution. So if you have considerable number of samples, any skewed distribution would be converted into normal distribution once you collect different samples and then take average of the samples and plot the distribution of the samples. Okay. What is the advantage of a two-tailed test versus one-tailed test? There's nothing. It's not about advantage. It's the question that you're dealing with. When you are trying to answer a question, say your hypothesis of certain value, my mean value should be 0. If your question at interest is whether to identify whether the data is actually 0 or not equal to 0, then you go for two-tailed test because the value can be either less than or greater than 0. But when you're interested to find whether the data is greater than 0 or less than 0, then you go with one-tailed test. So it's basically the question at hand. It's not about the advantage. What is p-value? I'll come to that, Sandeep. We'll discuss it in the next slide. Okay, let me continue with the session. I'll come back to these questions again. Right. So let's come back a bit, keep mathematics aside, and then see the procedure of hypothesis testing. Like right from conceptualizing your null hypothesis, how can you conclude your analysis, right? First step is that you determine your null hypothesis and alternate hypothesis. In the previous example, again, we have used mu equals to 14. This is my null hypothesis, where my alternate hypothesis mu is not equals to 14. Okay. Once you come up with your null and alternate hypothesis, you verify the necessary conditions that are satisfied and choose a significance level. Now, what does this mean? In the previous slide, yeah, this one. So I'm talking about this region as a critical value, right? This value is called the probability. The area after this is called significance value, the probability that, or the proportion of the of this area compared to the entire distribution, right? Now, once you get this critical value, we need to have a threshold at hand, which tells us that you need to have threshold at hand, which tells us that if the value that we are getting is above this, then you reject or you accept, right? Now, this is called significance value. Okay. So how do you choose a significance value? It is completely on the researcher's hand, but industry accepted, like most of the people that you see, is that you see 0.05 as the significance value, or 5% as a significance value. We'll talk about this with an example in the next slide. I'll come to that. Now, once you come up with this significance value or the threshold to accept or reject your null hypothesis, you identify the critical regions. Like if this is the if these are the critical values, if my data point is falling in this region, I reject the null hypothesis. So these becomes my critical regions. Okay. After that, you compute your test statistic, just like your z-score, which is x minus mu by sigma, as an example. Once you get this value, right, like you have a z value, and you see if z value is falling below the critical region or above the critical region in this case. If yes, then you make a decision whether to reject or accept your null hypothesis, and then apply this math. So this till this point is it's just numbers, right? Now intuitively, I interpret this decision to the context of a problem. If you're drug manufacturing, should you go ahead with your manufacturing process because you find the results accurate or according to the behavior, or should you revisit your composition or the manufacturing procedure or not, right? You interpret that decision in the context. So that's generally a six-stage process, right from conceptualizing your hypothesis to concluding your result. Okay, now let's take this example. We'll work out this problem, and then hopefully things are clear by this. Okay. College A has an average SAT score of 1500. Okay. From a random sample of 125 freshman psychology students, we find the average SAT score to be 1450 with a standard deviation of 100. If you take these two statements, right, my null hypothesis here is that average score is 1500 for the university, okay, for the college A. But this is assumed to be true. This is my general belief that 1500 is the average score. As part of the experiment, you have identified 125 students, okay, and you have seen that their average is 1450. Now this is my population mean, and this is my sample mean. I denote it by x bar c, and this by mu. Okay, and you know that the standard deviation is 100 for this sample. What does this mean? On average, so this becomes the representative of the 125 students, right? 1450 is the average. But when you look at the spread of the data here, the score by these 125 students, you know that the standard deviation is either you can see the values from 1550 to 1350, right? This is the standard deviation. The values will definitely range above 1350 and below 1350 and above 1550. But in general, you find data to be distributed like this. Most of your data like this. Okay, so that's given in the data. Now, what are we trying to find here? We want to know if these freshman psychology students are representative of the overall population in terms of SAT score. What are the hypothesis and test statistic? Okay, so the problem at hand is that I have taken 125 students into consideration. I have taken the sample mean, but is it representing the actual hypothesized mean value according to my general understanding? If yes, then we accept the hypothesis that yes, my college A is having students with a SAT score of 1500. If not, then this hypothesis value about the college A is wrong. So average score is not 1500 in general, but it is something else, and you need to recalculate that, revisit that. Okay. Now let's solve this problem step by step and complete the entire hypothesis test. Okay, so my mu again is 1500. The number of samples is 125 students. My sample average is 1450, and my standard deviation or the sample deviation is 100. Okay, we know that z score is x minus mu by sigma by root n. Okay, so this is the formula. What we do now is we substitute this. X is 1450 minus 1500 by 100 by root of 125, which gives me value of minus 50 by 100 by 5, close to this would be around 5.5 meters, or no, 2500 by 100 would be 25, right? That's my z-score. Sorry, right? That's my z-score. Now, what do we do here? There's something called z-table, which tells us that what is the probability of finding probability of this proportion of the data once a critical value is given. In this case, let's choose that our extreme region, right? My acceptable threshold is alpha 0.05. Okay, which means that if I find my average value to be in this distribution on the extreme 5% end of the data, either on the lower side or on the upper side, if my z statistic is falling in this side, I reject my null hypothesis. Okay, if you look at the z table, these values would be 1.96 and this would be minus 1.96. Okay, 0 being your mean value, you have 1, you have 1 here, minus 1. So this becomes my critical value. Okay, and if my z statistic is coming to be above this region, then I reject. If it is greater than, my z static is greater than 1.96, or if it is less than minus 1.96, I reject the null hypothesis, saying that my hypothesis mean is not 1500 but it is something else. Okay, so I'm not clear with the explanation on one-tailed versus two-tailed tests. Okay, I'll deal with that with two examples. This is one example which is having one-tailed two-tailed test. I'll deal with one-tailed test in the next example. All right. So the z score that we have calculated here comes out to be minus 5.59. Just do the math here. It comes out to be minus 5.99, which is again 1 second, minus 50 by 100. So yeah, so the z score is 25 here. So my 25 value is way above than 1.96, which is at the extreme end. So my average value is not 1500. So what is my conclusion? I conclude that the average SAT score is not 1500, right? So this becomes two-tailed test because we are looking at both the ends. Either the average score can be less than 1500 or greater than 1500, right? Let's take another example here. Now this is an example of one-tailed test. A farmer is trying out a planting technique that he hopes will increase the yield of his pea plants, right? Over the last 5 years, the average number of pots on one of his pea plants was 145. So his general assumption is that for each pea plant, right, the average number of pots that he finds is 145 with a standard deviation of 100. Okay, so in general, it can be either 45 pots per plant or it can be 245 with an average value of 145. Okay. Now this year, after trying his new planting technique, he takes a random sample of 144 of his plants. So what is my sample number? It is 144 data points. And he found that the average number of pots to be 147. Okay, so he wonders whether or not this is statistical significant increase, right? Here we are dealing with increase. We are trying to answer the question whether the data at hand, the sample, is suggesting an increase in the pot or it is the same. It's not talking about the decrease in the number of pots. So this becomes our one-tailed test. Previously it was what? We were trying to look whether the average score was 1500. We're not trying to see whether it is less than 1500 or if it is only less than or if it is only greater than. We are okay with both sides, right? So depending on the question, you select one-tailed or two-tailed, right? Now in this case, what are his hypotheses and the test statistic? Whether can he rely that since he has found based on 144 samples, he has found that instead of based on 144 samples, right? Instead of 145 pots, he has on average found 147 pots. But is this 144 number of samples sufficient to conclude that whatever new planting technique that he has come up with will work on every plant if he applies this technique, right? So if you look at the idea, right, if you look at the intuition behind it, they're essentially trying to see whether the average value or the effect of this particular technique is by chance or is it really producing some effect. Okay, let's solve this as well. So coming to the z value, x bar minus mu by sigma by root n, right? So this turns out to be 147, which is the sample mean, minus 145 by 100 by root 144. Okay. Now, if you calculate the z score, this would come something. This would be around 0.24. I'm sorry, I mean, yeah. So this would be around 0.24. Okay, now keep this at hand, keep this aside. Till now what we have done is have substituted our values in this formula. Now let's choose a significant value. As I said, once we get this value, we need a threshold to identify whether this is falling within the range or above the range, right? So again, coming to the normal distribution, which is, this is our mean, taking 5% as the significance value, which means I'm looking at the 5% of the extreme end, right? In this case, we're dealing with the increase in the data, right? So selecting the right region, this becomes my 5% of the entire proportion. And if you look at the Z table, this value is assumed to be 1.645. Okay, the value here, 1.645. Now, what is the value that you got? 0.24, right? So 0.24 falls within this region, below 1.645. So your Z value is less than your critical value. Clear? Which means we are failing to reject our null hypothesis. What is a null hypothesis here? Our null hypothesis is that the Planck technique, even though you apply the Planck technique, the average value will be 145, right? And your statistics suggests that you don't have any significant increase in your average value after this, and since it's falling within this region, you are failing to reject a null hypothesis, which means that your planning technique is not actually working on your plans. It is just by chance that you found the average to be 147, but it is not statistically significant, right? But what if your z-score has come out to be 2? In this case, the z value would be somewhere here. The difference between your hypothesis value and your data suggested value is kind of very large than the acceptable threshold. Then you say that your Planck technique, that the Planck technique that the farmer has applied is actually making a difference on the plants, right? So what do we conclude by this analysis? We say that whatever planting technique is there, it's not actually working on plants. The defect is not as huge as expected, and your null hypothesis failed to be rejected. Okay. How did we get a critical value of 1.65? All right. So the critical value here, right? Hello. Okay. The critical value in this case comes from a from a z table. For any statistic test, right? There are z table. There are tables. For z test there is a z table. For t test there is a t table. For chi-square test you find a chi-square table as well. In that case, what you do is you go to the table and you identify. So since 0.05 is our significance value, you look at the you look at the z-score value for this probability value, right? There you get 1.645. Okay. I can probably show you. Just let me grab the z table. Hope you can see this, the table. So all right. So based on the probability value, right? Since 0.05 is taken as the extreme end, right? Subtract 1 from that. If you're looking at 0.95, right? You take a corresponding probability value, and then you look at the row and corresponding row and columns in the z table, and that's when you get your z statistic. So for the probability value of 0.9945, the z statistic is 2.54. Okay, 2.5 first, and then the second decimal would be 4. Similarly, for the probability that we have considered here, which is 0.05, our z statistic would be coming down to 1.645 from the table there. Okay. So after dealing with the two examples, right, we came to know that how do we conceptualize a hypothesis, how do we come up with a significance value. Significance value is our understanding. It can be 0.05, can be 0.01, can be 0.1. It depends on the researcher. And then we compute the statistic from the sample distribution, and then check how different is the sample from your hypothesis value. And if it is very different, you reject your null hypothesis. And if it is within the acceptable region, you fail to reject your null hypothesis. Okay. Now, p-value. Let's come to this. This is again, if you look at the formal definition, assuming the null hypothesis true. So whatever my basic assumption is there, right? Like my drug manufacturing example where the mean of active ingredient is 14 milligrams. Assuming that that is true, what is the probability of getting a statistic number which is very far from 14? Okay, so that is called p-value, and based on that p-value, and taking significance value, you can either reject your fail to reject your null hypothesis. I know it's too much to take, but let me deal with this with an example. Consider the same probability distribution like this. Okay, I have my mu here, mean, my z statistic, right? The critical value is this, which is say 1.645 in the previous example. How did we get 1.645? It is just dependent on the significance value that you are selecting. It's not dependent on the sample data distribution. So for 5% for the 5% significance value, my z score is 1.645, which is here. Okay. Now, as in the previous example, right? As in the previous example, I have my data points. Say we have collected 30 data points. We have got the z statistic to be somewhere around here from the sample data, right? My data is somewhere here, which is says 0.9, my z value. Okay. Now, what is p value? P value is the probability of finding a number greater than what you got. So the entire region which is marked by white, right, white shade, is the p value. This is the probability value that given my null hypothesis is true, the probability of finding z statistic or the data distribution greater than 0.9 is this. Okay. Now, if you see, my critical region is this. I have my critical value of this of the data distribution to be this region. I know that my p value is greater than the critical region or the significance value. So my p value here is 0.9, say, or 0.09, intuitively correct, and my significance value is 0.05. Okay. Now, if my p value is greater than my significance value, you fail to reject the null hypothesis because it is in the acceptable region. It is falling in the acceptable region, right? A similar example, let's take the same scenario where you have mu, your critical value is 1.645, and your z statistic came out to be 1.8. Okay, so 1.8 value will be somewhere around this. Okay, and your p value for this 1.z statistic, say, would be 0.02, the probability, right, in this region. Okay, if you observe the difference between significance value and the p value, it's important to understand. Significance value is your significance value gives the probability where the region is above your critical value or below your critical value if it is two-tailed test. But p value comes from your data distribution, from your sample. After getting a sample, you calculate your z statistic and look at the probability of extreme ends from that, right? And see the probability that you find, which is 0.02 in this case, if it is less than the significance value. Now, in this case, it is forming at the extreme end, and as we said, if it is falling above the significance value or the greater than the critical region, we reject the null hypothesis. So in this case, we reject it. Okay. So instead of calculating the entire z-score, going to the z-table and coming to a conclusion, we can simply use p-value, and there are statistical packages available both in R and Python, where you just input your data and you get your statistic values and output along with the p-value, right? So just based on the p-value, if it is less than your significance value, usually we select 0.05. If it is less than the significant value, you reject your null hypothesis. And if it is greater than the significance value, you accept the null hypothesis, right? A simpler way of analyzing your hypothesis result rather than going and calculating the entire test statistic and going to the z-table and coming up with conclusions. All right. Since we are running up on the time, I'll just touch upon this concept further. Let's say, still now what we have done, we know that we have assumed something from the population. Okay, that this is a general behavior from the population, and we have used sample from this population, and we have studied the characteristics of this sample, and then we came to a conclusion about the population, right? So this was the general intuition behind the discussion till now. Now, confidence intervals work in a different way. What we do is we first collect sample. Okay. And with certain degree of confidence, say 95% confidence or 90% confidence, we say that whatever value that we have found, whatever statistic that we found from the sample, will lie within will lie within a certain range, right? This range comes from the sample, right? This range comes from the sample, and we attribute this to a population. Clear? Let me talk about this with an example. Let's say that a sample distribution, we have a mu value, right? We have, say, 30 samples. We calculated the sample mean from this. Say it has come somewhere between 12, right? The sample mean is 12. Now, what I would now try to do is, since my mean value is 12, I want to state with certain degree of confidence, say 90% of the confidence, that since my sample mean is 12, I would say that with 90% confidence that my population mean also would be lying in this range. Now this range represents 90% of the area under the curve. Okay, so I'll be rejecting the extreme 5% here. I'll take the middle 90%. I'll see the range here, and I say that with 90% confidence, I'll be with 90% confidence, the population mean would be ranging between these ranges, with the mean value probably close to 12. Okay, so in this example, as it is mentioned here, with 95% confidence interval, the population mean is between 72.85 and 107.815. Okay, now how does this 95% come up? It's again it's again under our discretion which confidence interval we need to take. If it is 99%, what would we do? We go to a rather more extreme ends. If it is 80%, our region of interest would be decreasing, right? So as our confidence decreases, our range also decreases. Right? That's what confidence intervals gives us. It gives us an idea about the population parameter by studying the sample statistic. Now, as we're dealing with the hypothesis, right? Like there are 4 cases that you can broadly look into. One is your null hypothesis can be true or it is actually false. Again, taking the example of 14 milligrams, right? My null hypothesis of 14 milligrams, if it is believed to be true, we get under these conditions. But if my assumption is wrong, now my null hypothesis itself is false, which is actually the 14 milligrams is not correct, but it is somewhere around 12 milligrams or 16 milligrams, right? So my null hypothesis itself is false. So under these 2 different conditions, we have 2 possibilities. Either we fail to reject the null hypothesis or we reject the null hypothesis. Okay. Now this gives us 4 cases. Okay. Now when the hypothesis is true and you fail to reject the hypothesis, which means my critical values are here. Your hypothesis is true and the sample statistic is falling in this region, right? In this region. So which is a correct decision. So you're good with this decision. Okay, when your hypothesis is true, you should be failing to reject your null hypothesis. Similarly, when your hypothesis is false, you have to reject your null hypothesis, right? Like suppose if actually the active ingredient composition is not 14 milligrams, but it is something else, and after conducting your experiment using statistics, you assume even your statistics told you that the null hypothesis is false, then you again came to a correct decision. But the problem is these 2 cases, right? When your hypothesis is true, but you're rejecting hypothesis, then that is called type 1 error, which is alpha. And this alpha is nothing but the significance value that we're talking about. Okay, so this probability, right? This is called alpha. This is type 1 error, which means your null hypothesis is actually true, but your sample is giving you a number which is very extreme, that even though your hypothesis is true, you're rejecting your hypothesis, right? You're actually rejecting a hypothesis when you should not. So that gives you type 1 error. The second case, when your hypothesis is false but you fail to reject. Say actually my mean is not 14. Practically speaking, my mean is say somewhere around 12. But after conducting an experiment, you're getting your sample data with mean 13 and it is within the acceptable region. So even though you have to reject your null hypothesis, you are failing to do that. So that's when the type 2 error occurs. Okay. So you need to be careful with these two types of errors, and then take your significance value in such a way that you convey your results with greater confidence. Okay. All right. So that's with z-test, I guess. Right from conceptualizing your hypothesis, defining your null hypothesis and alternate hypothesis, coming up with a test statistic, and seeing if it is falling in the extreme regions of your probability distribution. If it is at the extreme ends, you reject your null hypothesis. If not, you accept it. Right now, that's z-test for you. But there are different kinds of tests available, namely t-test, chi-square test, and f-test, which are again useful in different scenarios. Briefly speaking, z-test is used when your sample data has more than 30 data points, right? And when you know about your population distribution, like I talked about the standard deviation, right? When you know the standard deviation of your population, and when your data points are more than 30, you can use z-test. T-tests are similar to z-test, but these will come in handy where your data points are less than 30, or when your population standard deviation is unknown. Okay, I'll not get into specifics since we're lacking in time, but based on the data, right? Like first you need to understand like what is your sample size, what parameters or what information you know about the sample and the population, and that's how you can select which test to apply. Okay. So z-test and t-test, f-test, these are all numerical tests based on which work on numbers, but chi-square tests work on categories. Okay, so I'll deal with simple example in the next slide for chi-square test, and then I think we'll take questions if there are any. So till now we were looking at one particular data type, one particular drug sample, or one particular election results, or the average scores scored by students, right? So which are numbers. Now imagine a scenario where you're trying to conduct a survey, and you believe that the female population is more inclined towards Democratic Party rather than the male population, right? Now this is your hypothesis, which you want to check, right? So in this case, my null hypothesis would be there is no effect of gender on the selection of the party, whereas my alternate hypothesis would be female voters would prefer Democratic Party more rather than Republican Party. Okay, so that's how we come up with the null and alternate hypothesis, right? Now in this case, how do we come up with the conclusion? What chi-square does is it analyzes the pattern between these numbers, like these four numbers that you see here, right? It checks whether the distribution in this is there a pattern which is above an acceptable threshold, above the expected value, and if yes, then there's a definite relationship between gender and the party that the voters select. Okay, if not, then we say that the vote to Democratic or Republican Party is independent of the gender. Okay, so that's how chi-square test helps us. It helps us to get to conclusions with the categories at hand. So chi-square test can be used in two different scenarios. One is to understand the goodness of a fit. So say you have only one category, right? Democratic Party, and you have gender at hand. Okay, so 50% of the male voters are voting Democratic Party. 60% of the male voters are voting for the Democratic Party, right? So is this acceptable? So this is the observed value, right? And there is something called expected value that you usually expect. Like 50, in this case, it would be half of the population would be closer to Democratic Party, and half of the population of male would be choosing Democratic Party, right? Now we will see how different is the observed values from the expected value using this formula, using these two formulae, and we come up with the statistic called chi-square. I'm not going into the mathematics, right? And if this chi-square statistic is greater than the critical value, right? If this is greater than the critical value, then we come to a conclusion that the effect the goodness of the fit is not as expected. Okay. Similarly, when you look at the test of independence, this example comes in handy, where you have two different categories, and your base assumption would be, your null hypothesis would be, gender is independent of voting. Okay, independent of party selection. where your alternate hypothesis gender is dependent, or your party under selection is dependent upon the gender. So in this case, you're trying to test the independence of these two categories, gender and the party, right? So chi-square test helps in these two scenarios. All right. So this is the last slide. One of the questions was regarding how was hypothesis formulation useful in machine learning model building, right? So those are of interest, right? Those are not linear regression. What we try to identify is, suppose say that we are trying to so this is the weight of different persons. This is the data that I have. Okay, about seven samples here, and this becomes my input. Say I'm trying to identify the height of the person based on their weight. Okay, now X becomes my independent variable here, talking in terms of regression, and Y becomes my dependent variable. Okay, so what am I trying to do here? I'm trying to predict the height when I only have weight at hand. Okay, so if I plot weight, say this is 140 to 250, and this is my x-axis, and I plot the height on y-axis, right? So this is somewhere around 50 to say 80. The data is something like this. Okay, you find a linear trend here. Even though the points are a bit scattered, you find a linear trend between height and weight. So there's a linear relationship that you can say, which is found between weight and height. As weight increases, you know that your height increases in general. There might be certain outliers, certain points which do not follow, but in general, you find a linear trend here. Okay. Now, without applying any mathematical technique or any regression model or any machine learning model, if I ask you to say predict height, a simple thing that I can do is take an average of the height in the data, and then say that this is my predicted value. So irrespective of the weight, I say that my height would be on average say 70. This is the average from the data, right? So irrespective of the weight, even for 140 I predict 70, even for 212 I predict 70. Okay. So that is without any math, any regression model. I'm just using an average of the weight from the average of the height from the sample that I have. Okay. So if I take that as example, right, like my y is 70. If you remember the straight line equation, it is alpha plus beta x, or y equal to mx plus c, that we have studied in our schools, right? Where x is the value of x-axis, the value on the x-axis, c is the y-intercept, right? And m is the slope. Okay. Coming back to the previous assumption, if I take y value to be 70, what I'm trying to do is, this is equal to 70 plus 0 of some x value. Okay, so in this case, my slope is 0, or beta is 0, and my c value is 70. Okay, so without applying any regression model, my regression equation, without applying any complicated math, my regression equation came out to be y equal to 70, which is this horizontal line. Right? Suppose, taking the trend into consideration, okay, my regression model, there are certain optimization techniques that are playing in hand, and you come up with certain equation which will try to generalize the behavior of predicting the height with respect to weight. And suppose this is the line that has come up with, the model has come up with, which is say y equal to 70 plus some 0.1 into x value. Okay, this is my equation, y equal to 70 plus 0.1 into x. Okay, in this case, your beta value is 0.1, and in this case, your beta value is 0. Okay, when your beta value is 0, as in this case, you are saying that there is no relationship, absolutely no relationship between your x variable, your independent variable, and your dependent variable. Okay, so my null hypothesis in this case would be my slope is 0, which means there is no relationship. Okay, whereas my alternate hypothesis is that my slope is not 0, which is in the second case. In this case, my slope is not 0. There is some 0.1 slope, which suggests that my the values of y are definitely dependent upon the x, which means as x is increasing, the y is also increasing, right? Correct? In this case, no. As x increasing, the y value is remaining constant. Even though you take x to be 140 lbs or 212 lbs, my y value is not changing, right? So there's no relationship between y and x. But in this case, if your x is increasing, your y is also increasing. So there's definitely a relationship. And how can you quantify that relationship in this equation? The value of slope or with the value of beta. So that's how I'm conceptualizing my hypothesis here. Okay, now what you do after coming up with regression model, say your regression model is somewhere like this, your equation is like this, y equal to some 0.1x plus 70. Okay, now how can this hypothesis test help us? It can tell us whether the slope that is in hand, right, is it actually representing the data, or is it actually predicting the y value correctly, or do we expect the slope value to be a bit higher? So as you know, if this is the trend, you can have a regression line like this, or you can have a prediction line like this. Okay, now whatever slope your data is showing, is it statistically significant enough to base your conclusion that y value is dependent on x, or is it not that statistically significant? Okay, so that's how you can use hypothesis testing even in regression models or even in your machine learning models to come up on conclusions after evaluating your models, after coming up with your model equation. Right. So summing up, what we have done, we have seen what is population, what is sample, how do we sample data, why is it important to collect samples which is a good representative of all the subcategories in the population. And once we collected sample, we come up with a significance value or the acceptable threshold, I would say, above which, if your sample is suggesting your data is above that acceptable threshold, you reject a null hypothesis, and if it is not, you accept the null hypothesis, right? And there are different techniques like z-test, t-test, f-test, chi-square test, depending upon the data at hand, depending upon the kind of question that you want to solve. You would select a test and then go about it. So that's from my side. If you have any questions, I think there are a lot of comments. I'll try to answer these questions, and if you're interested, you can stay back. How to decide null hypothesis? I think I've answered most of the questions because they are posted previously. So why not 99% is one of the questions. So it's up to your choice, Ashish. So as I said, it's on the researcher's discretion which significance values you have to choose. No, but understand this thing. So if you're selecting 95% as the significance value, or the 5% as the significance value, and your acceptable value, range is 95%, compared to your 99%. Okay. If you're selecting 99%, you would only be left with the top 1% or bottom 1%, or if it is two-tailed test, bottom 0.5 and top 0.5%, right? As the rejection regions. So you're confining your your analysis to a very restrictive zone. Okay, whereas 95% gives you a better spread of the data. Whereas your rejection regions are also of good quantification, not just 0.5% or 1%, but you have 5% of the values which are falling in the rejection region, right? And it's again dependent on the data at hand and the question that you're trying to solve. If it is drug discovery, right? If there's an application like drug discovery, you cannot do a mistake, right? So you can probably select 99% as your significance value, or the 1% as significance value, because you want to be very confident about your statistic, right? If it is not that important, if you're trying to do something about the election results, or if you're trying to do something on the manufacturing defect side, right, then 95% is feasible. So it's upon our interest. Thanks a lot for joining. Have a great rest of the day.